Hey everyone, welcome back to the channel. Today I'm going to teach you about 16 of the most important statistical distributions. Each probability distribution packs a lot to work with. The notation, the parameters, the PDF and CDF, the mean and the variance, and way more. All of these are extremely useful, but difficult to know by heart. Luckily, unless you are a mathematician, there is really no need to memorize all of these. This image is from Wikipedia, where the details of each distribution is written 2 clicks away. The trick is to know at which distribution to look at. There are so many of them. Well, for that, the best approach, in my opinion, is to know the story of each distribution and how it connects to other distributions. Our journey begins with a single coin toss. We don't know which side it will fall on, and this will be our source of uncertainty for several extremely important distributions. This very basic experiment, one with only 2 possible outcomes, gives us our first probability distribution. It is called the Bernoulli distribution, after the mathematician who formalized it. And it tells the story of an experiment with only 2 possible outcomes, heads or tails, success or failure, 1 or 0. Moving forward, I will use the coin example, but it works the same for any experiment with 2 outcomes. The only parameter for the Bernoulli is p, the probability of one of the outcomes. Usually, the other outcome's probability, 1 minus p, is denoted q. But what if you tossed multiple coins, one after the other, or the same one multiple times? Some will land on heads, and others will land on tails, but each of these tosses is an independent, identical Bernoulli experiment with the same p probability of heads. But what can we say about the overarching experiment of tossing n coins, each with probability p? The most basic question to ask is, how many heads do we get? And that's exactly what the binomial distribution is dealing with. It has 2 parameters, p, the probability of heads, in each toss, and n, the number of tosses. And it answers the question, how many heads will we get in n independent tosses, each with probability of p to get heads? For example, if n is 5 and p is 0.3, the binomial distribution tells us 1 head is the most likely outcome with probability of almost 0.4, and 5 is the least likely. But there are other interesting questions we can ask about the situation, such as how many tails until we get the first heads? For that, we have the geometric distribution, and it gives us the probability of each number of tails before the first heads. For example, with p equals 0.3, having no tails at all before the first heads is the most likely outcome, with probability 0.3, which is p, obviously. This distribution has a very useful property, memorylessness. This means that if you have 3 tails in a row, you are not more or less likely to get heads now because of all of the tails you got before. There is no memory of the past. It doesn't affect the future. Even after a million tails in a row, the probability of heads is just what it was in the beginning, p. Visually, it means that if you cut the beginning of the distribution and look only on what is left, scaled so that the sum of the probabilities is 1 again, you will get the same exact distribution. But why count tails until a single head? We can generalize the question and ask, how many tails until we get n heads? Not necessarily in a row. This generalized version of the geometric is called the negative binomial distribution, which is not negative and also not binomial. It has two parameters, p, the probability of heads in each toss, and n, the number of heads at which we stop tossing. It answers the question, if we just toss a coin over and over, how many tails we get before accumulating n heads. For example, if we want to count to 5 heads and each single toss has probability of heads 0.3, the most likely number of tails is around 8 before getting 5 heads. Of course, you can think of the negative binomial as several geometrics, one after the other, since the number to the, for example, third heads is the sum of the number of tails to the first heads, plus the number of tails from that point to the second heads, plus the number of tails from the second heads to the third. Of course, we can also generalize the fact that we toss a coin with only 2 outcomes. Instead, we can toss a dice with x possible outcomes instead of only 2. The multinomial distribution generalizes the binomial into multiple outcomes. The first parameter is n, number of tosses, just like with the binomial. But the second parameter is now a vector called p that specifies the probability of each outcome. If it's a regular fair 6-sided dice, there will be 6 elements for this vector, one for each outcome with equal probabilities. If the dice is loaded and not fair, the probability of each side will be different, but they will always be between 0 and 1, and they add up to 1. This distribution tells us how much of each outcome will we get after n tosses of the dice. Before we move on, I would like to discuss one distribution that doesn't fit into the coin tossing family, and it is more of a neighbor to it. The hypergeometric distribution. Don't let the name fool you. It is not a hyper version of the geometric distribution, it's just that mathematicians are bad at naming stuff. It answers the question, if you draw at random n marbles from a bag with b black marbles and w white ones, how many white marbles will be in your sample? On first glance, it might seem to be just the binomial again, but with marbles instead of a coin. You still have a series of trials, each with 2 possible outcomes, heads or tails, black or white. But the difference is that in the binomial, the chances of heads is the same each time. In the hypergeometric, on the other hand, if you pull a white marble, then now there is one less white marble in the bag, so your chances of getting another white one is lower. But it is true that when b and w are large enough, taking out several of them doesn't change the ratio between the groups in a way that is meaningful, and therefore the hypergeometric approximates a binomial. Let's recap the coin tossing family of distributions, shall we? We have a sequence of n coin flips. Let's, for the sake of the example, let n be 9. Every single coin flip is a Bernoulli distribution, with p being the probability of heads. The probability of getting any number of heads is given by the binomial distribution, while the geometric deals with how many tails will you need to get the first heads. Its generalization, the negative binomial, counts the number of tails before you get k heads. The multinomial expands the binomial to the case when there are more than 2 outcomes possible at every trial. And lastly, the hypergeometric will give us the number of white marbles from a bag with both white and black ones. Our next family of distributions have a slightly different story. Instead of a sequence of distinct independent trials, we have a period of time at which some event can happen multiple times. For example, during a single hour at the office, a manager can get any number of emails from 0 to, theoretically, infinity. The probability to get a mail in any specific single moment is very, very low, but since there are a lot of moments in an hour, at the end of the hour, some mails will be received. The probability of each possible number of mails at the end of the hour is given by the Poisson distribution. It has one parameter, lambda, which is the expected value of emails. You might say that this is just a binomial with high n and low p, and you are right. Without getting too much into the mathematical rigor, when n goes to infinity and p goes to 0, a binomial becomes equivalent to the Poisson. Here, in this image from Wikipedia, you can see how it looks like with several choices for lambda. Another useful question in this scenario is time until first email. For this, we have the exponential distribution. It has the same parameter as the Poisson, lambda, with the same intuition. You can think of lambda as the rate or intensity of the process of emails getting into the mailbox. Note that the exponential is equivalent to the geometric distribution that dealt with how many distinct trails we need before first heads. Here we don't have distinct trails, but instead a continuous timeline. And just like the exponential is the equivalent to the geometric for continuous timeline, the gamma is the parallel to the negative binomial and generalizes the exponential to ask how much time to the nth email. Just like the negative binomial was a sum of geometric distributions, the gamma is a sum of exponential, and we can set the parameters of it accordingly. Note that alpha and beta doesn't have to be integers, and with different value combinations of the gamma, it can relate to many other distributions, connections that are beyond the scope of this video. The next two distributions strongly relate to the concept of probability of probabilities. Let's say you are asked what is the probability of you winning a chess game against a mystery player. Well, since you know nothing about the strength of the opponent, a reasonable answer will be that every probability of winning is just as likely. More formally, we would say that the probability of winning is just as likely to be in any one interval as the other as long as they are in the same length. To express this idea of all numbers in a range are just as likely, we use the uniform distribution. It has two parameters, a and b, that specify where the interval of possible values start and ends. When a is 0 and b is 1, we get the most fundamental form of the uniform, that conveys the idea of total lack of prior knowledge about what is going to happen. Each draw from this distribution is a non-negative between 0 and 1, and therefore will be a valid probability. Back to the chess example. Let's say you play this mystery player 3 times and win 2 of them. Well, now we have some data, and we can therefore change our beliefs on which probability of winning is more likely. We know that winning probability of 0 has probability of 0 because we won 2 games, and probability of winning of 1 is also impossible since we lost 1 game. And since we won 2/3 of the games, we know that the winning probability 2/3 is the most likely. To express beliefs about the probability of each probability, we use the beta distribution. As such, it will always be set on the interval 0 to 1. Like the gamma, it has 2 parameters, alpha and beta. They control the shape of the distribution. The beta has a very strong connection to the binomial, since it gives a closed form to the probability of P for every combination of heads and tails. Simply plug alpha minus 1 equals number of heads and beta minus 1 as the number of tails, and you get it. For example, if they are equal, the most likely P is 0.5. And now we finally reach the most famous, central and important distribution in statistics: the normal distribution. It is so fundamental that it has two other common names: the Gaussian distribution and the bell curve. Many things in nature are modeled by the normal distribution, like IQ and height. The distribution of measurement errors are usually considered to be normal in statistical analysis. This distribution appears anywhere once you start looking for it. It has two parameters: mu, which is the mean, and sigma squared, which is the variance. And it looks like a bell, which is why it has the name bell curve. In this image from Wikipedia, you can see how mu controls where on the number line the apex of normal will be, while the variance controls how spread out it is. The normal distribution can be used to approximate a binomial with p close to 5 and large n. Here you can see a binomial in yellow and the matching normal curve approximating it. It can also approximate the Poisson when lambda is large. In the image you can see how the Poisson becomes more and more bell-like as lambda increases. Another amazing fact about the normal that contributes to how important it is the central limit theorem. It says that if you take large enough samples from any distribution and use the means of the samples to build a new distribution, it will be approximately normal. To visualize this better, I highly recommend playing with various distributions and their sampling distribution in the site Thing Theory. I will link to it in the description. The reason this theorem, and the normal because of it, is so central is that the whole field of statistical testing is based on sampling and comparing means to determine if an effect is significant. The t-distribution is close to the normal and is derived from it. It is like a normal distribution, but has mean 0 and variance of 1. The parameter v decides how heavy the tails are. As you can see, as v increases, the tails are thinner and the peak higher. When v reaches infinity, the t-distribution is equivalent to what's called the standard normal, a normal with mean 0 and variance of 1. The t-distribution is used extensively for statistical testing, like comparing a sample to the population of unknown variance, and comparing two samples. The next and final distribution today will be the chi-squared. It has one parameter, k, which is the degrees of freedom. It controls the flatness of the curve. The higher, the flatter. I'm not going to get into what degrees of freedom are. It's beyond the scope of this video, maybe in the future. We use it mainly for testing how significant is the difference between a sample and a population when the distributions are discrete. For example, is the distribution of favorite cars is the same in a certain city as the whole country? Since favorite car is a discrete categorical choice, we use the chi-squared distribution to test it. And with that, we reach the end of this video. Thank you for listening, and I will see you at the next video. If you want to be notified when that happens, please subscribe. It really helps me out with making of these videos.